Now, one of the things that happens when we have increases in temperature, decreases in temperature, etc., is that things tend to expand when it gets hotter, things tend to contract when it gets colder, okay? And that's actually how a thermometer works, right? If we think about what a thermometer looks like, we've got, you know, this glass tube that typically has some type of bulb at the bottom, and, you know, liquid up to some place here. And if we heat this up, if we hold on to this, the temperature rises. Well, it's just that liquid is expanding, right? And if we put it in the freezer, that liquid contracts down in the bulb. And as a result, what we end up with is we end up with being able to put a scale along that and tell what temperature it is. Now, just in general, that works with basically all objects have some level of expansion or contraction that goes on when they heat and they cool. And the change that we get in the length, if we're talking about something that's largely a one-dimensional object, change that we get with length depends on how long the thing was to start with. Okay, so if you think about like a railroad track that's, you know, very, very long and made out of metal, it's going to expand a bit as it goes through cold and hot in the outdoors. And so they lay tracks of a certain length, and then they leave a small gap. Small enough gap that a train goes right over it, doesn't even notice it's there. But it's a small gap so that when it expands on the hottest day that they could possibly get, those tracks aren't running into each other, etc. So they have some particular length, how much of a change in temperature there is, and then there is a coefficient. And that is just, in this case, it's called a linear expansion coefficient. And in the same way that when we talked about resistance, different materials have different resistances, different materials have different coefficients of linear expansion. So some things expand more than others as it gets cold or hot, and there are tables, somebody has spent the time and stood in a lab, said we're going to heat this thing up by 10 degrees. How much does it expand? It wouldn't, 10 degrees wouldn't be enough. Heat it by 100 degrees, does it expand? Heat it by 200 degrees, does it expand? Taking new measurements, etc., to establish what these coefficients of linear expansion are. And so then you can say, okay, if I have a particular object, let's say that it's aluminum, you can look up in a table, what would be this linear expansion coefficient? And if I had 1 meter of aluminum and a temperature change of, 50 degrees, how much would I expect that to expand? All right, and there's also, usually we talk about linear coefficients of expansion. There are also both in area, so this is really a one-dimensional. This is talking about something that's long and skinny. You can ignore the other dimensions, but if we talk about something that's more or less, like say a sidewalk, where you have a sidewalk that's maybe 3 feet by 3 feet in terms of its size, then there's an area expansion that's going on. And the change in the area is again related to how much area you started with, how much change in temperature, and then there is an area expansion coefficient, which if I remember correctly is beta, typically, and that's a less common thing. No, I have it reversed. That's the volumetric one. It's a gamma. And again, that is an expansion coefficient for area. So 2 dimensions. And there's also one for volume. And for that one they use beta. And it depends on how much volume you start with and the change in temperature. And that is a volumetric expansion coefficient. So if you think about this, anybody who's ever mowed the lawn, you got gas in a can, and you leave it sitting out in the sun, you come back and the can might be all swelled up. Okay, that's because that volume of gasoline that's in there and the volume of air that's up above the gasoline, they're trying to expand because it got hot out in the sun. Or if you if you have that and you leave it in the refrigerator, why would you do that? I don't know. Sometimes I know you used to have a bottle of pop empty on the floor with a lid on it, and if you go out in a cold morning, well, it will shrink, and you can look and you can see that the bottle itself is kind of shrunken down, and that has to do with this contraction. So if the temperature goes down, this is going to be a contraction. This is the change in length, the change in area, the change in volume, and of course, if your change in temperature is negative, then this change is going to be negative. It's going to be a shrinking. And if your change in temperature is positive, then it's going to be an expansion. And let me do an example here where I talk about something. Let's see if I've got. So let's say I've got a piece of copper, 1 meter long. Some of the stuff out of the way. So I'm just going to talk about a linear case here. All the other ones would fall the same way, just depends on what kind of calculation you're trying to do. Let's say 1 meter piece of copper. And we're going to say that there's a change in temperature. The temperature goes from 55 degrees Celsius. That's too hot, isn't it? 35 degrees Celsius, which is very hot. We just talked about that. 30 was 86. So this is over 100 degrees. We're out in Arizona somewhere. And during the night, it falls from 35 degrees down to 15 degrees. Okay? That's a 20-degree fall. That means my delta T, in this case, would be 15 minus 35. Right? It dropped. It's going to be a negative change here, so that's going to be negative 20. Now, it turns out that for copper, the coefficient of linear expansion is 17 times 10 to the minus 6. And these are in appropriate units. So this is inverse degrees Celsius is what the units here are. And if I put those together, I say, well, how much is this thing going to grow? Okay, or how much is it going to shrink? I put 17 times 10 to the minus 6. I've got an L, well, initially it was 1 meter long. I've got a change of negative 20. The negative tells me it's going to shrink. Okay? And if I go 20 times this, I get 340 times 10 to the minus 6, which, if we move some things around here, we're going to say that's 0.340. And I can move the decimal 3 place to make that 10 to the minus 3. And I can say that's 0.340 millimeters. So that 1 meter long piece of copper would shrink by 0.34 millimeters. Very, very tiny amount, right? Now, that tiny amount is sometimes enough to make a difference. When they first were designing and putting things up in space, there were cases where they put together a piece of equipment that should have functioned in space, but they didn't take into account contraction. And on the outside of whatever's out in space, it's either going to be very hot if it's on the sun side, or very cold on the non-sun side. And so things would kind of flex, and you wouldn't get electrical connections you were expecting, etc. So they had to modify their designs in order to make things function properly. Also, if you've ever had a situation where, like, maybe you're cooking and cleaning up afterwards, and you put something in the sink and it gets inside something else and they get stuck together, like a glass inside a glass. Well, if you have that glass inside a glass situation, if you are able to cool down the interior glass while the exterior glass remains hot, then you'll be able to create enough of a gap that you'll be able to get the two apart. And I've actually had that situation before where I was able to do that. So that is expansion, and we'd have the same, that's contraction, and we'd have the same kind of thing with expansion. It would grow that much if it was reversed and we're going from 15 to 35.